Hey everyone, so I wanted to make this video to explain the process I'm going through to fix some drone in my exhaust. So I recently bought a car a couple months ago and the exhaust drones really bad at about 2000 RPMs to 2500 RPMs. So driving around in the city, that's pretty irritating. Doing some research online, I came across some different ways I could eliminate this drone. Number one being replace the resonator, number two being replace the muffler, and number three is what's called a quarter wave resonator, also called a Helmholtz resonator or commonly referred to as a J-pipe. First off, I'll just explain the reason why I'm not going to replace the resonator or the muffler is because while those may be effective ways to reduce noise in your exhaust, the problem is you don't know exactly what to expect by replacing these components. So the best you can do is look up a video of the product you want to buy, and maybe you can find a video of it on your car and get an idea of what it sounds like. But that's kind of the best you have, and then that's not really a very scientific approach. So I chose to go with the third option, being a quarter wave resonator. In this video, I'm going to explain to you what that is. I'm going to explain the engineering behind how it works, and I'm also going to provide you guys a tool so you can do the same calculations that I'm going to be doing on your own vehicle. So you can hopefully reproduce this if you want to do the same modification. Just a quick overview of the video. First, I'm going to show you a cold start of the vehicle, some driving shots, then a warm start of the vehicle. Then I'm going to get into more of the explanation of the engineering and all the math and why this works and how it works. And finally, I'll show you what's done to the vehicle, what the shop is going to do next week, and then some more shots afterwards, cold start, warm start, and some driving shots. Hopefully this video can give you a great understanding of what this modification is, and I'm hoping it can give you some confidence if you're wishing to do this to your own vehicle, that it will in fact work and that the method is sound and backed up by actual science. So let's get started with some before shots of the vehicle. that we have an idea of what the car sounds like, I'm going to explain what a quarter wave resonator is and how it works to reduce exhaust drone. So the first essential question is, what is a quarter wave resonator? It is a pipe that is calculated to be 1/4 wavelength of the frequency of your exhaust drone. So to draw a diagram of your exhaust, you have your muffler, then your main exhaust chamber runs the length of the car coming from your engine, with the exhaust gases flowing in this direction. Now, a quarter wave resonator, or a J-pipe, is a pipe welded onto your exhaust and closed at one end. And now you can see why it's commonly referred to as a J-pipe, because it is typically in the shape of a J. Now the ideal shape would be perpendicular, completely perpendicular to your exhaust, but due to space restrictions, that's not always practical. So a lot of people use a J-pipe. Now your engine produces many different tones of sound because it's constantly increasing and decreasing in RPM. We're going to represent those sounds by drawing a few waveforms. These 3 waveforms are of different frequencies, and they represent the different noises or sounds that your exhaust produces. So the length of this pipe is equal to 1/4 wavelength of the frequency of your exhaust drone. This symbol here is the symbol of wavelength. Now let's say that this blue curve, this blue waveform inside of your exhaust, is the tone that you want to eliminate. One wavelength is expressed as the distance between 2 humps of the curve, but you can use any reference point. So 1 wavelength can also be expressed as this distance or this distance. Doesn't matter what reference you choose, but 1 wavelength is 1 full cycle of the wave. Now the equation for wavelength is the speed of sound over frequency. And if you know the frequency of the sound, you can calculate the wavelength. And if you know the wavelength, you can calculate the frequency. This is the key equation in this application, and I will show you how to make this calculation later. But for now, let's stay focused on the theory. So we know what a wavelength looks like in terms of a sound wave. Now I'm going to introduce a topic to you called phase shift. This is a helpful diagram to illustrate phase shift. So a sound wave, or any type of wave, we already know can be expressed as wavelength. Now this sound wave can also be expressed in degrees. 1 wavelength is equal to 360 degrees. That you can see in this diagram right here. 1 wavelength of this blue curve is expressed as 360 degrees. Now, the second question is, what is significant about 1/4 wavelength? We already said that a wavelength can be expressed in terms of degrees. So let's do the calculation here. 1/4 wavelength expressed as 360 degrees equals 90 degrees. Let me redraw a picture of your exhaust. Remember, the gases are flowing this direction. And like we said, we have many exhaust tones in your, many sound tones in your exhaust. Now this blue curve represents the tone of the exhaust drone that you want to eliminate. And what happens here is the exhaust is flowing through the main chamber, but by adding this J-pipe, the exhaust is also going to flow into this added chamber. So let me draw a comparison between the exhaust tones in your main exhaust chamber and in your J-pipe. Remember, your J-pipe is designed to be the length of 1/4 wavelength, and that can be shown in this side-by-side comparison right here. So we already know that a wavelength is expressed as a full cycle of the wave. So that means that this distance is 1/4 wavelength. So I'm going to redraw your exhaust here. I'm going to draw the J-pipe as just this perpendicular pipe for the ease of understanding. So your exhaust waveforms are traveling through here at the speed of sound repeatedly, and also they are going into this J-pipe at 1/4 wavelength. They travel 1/4 wavelength into the pipe, they hit this wall, and they travel back out of the pipe. So the total distance traveled here is 1/4 wavelength in this direction plus 1/4 wavelength in the opposite direction equals 1/2 of a total wavelength. Expressing this in degrees, remember a full wavelength is 360 degrees. Expressing this in degrees gives us 180 degrees. So what is significant about 180 degrees? What you are doing is you are creating a phase shift of the sound in your exhaust. You're phase shifting the wave by 180 degrees by making the wave travel an extra 1/2 wavelength in the J-pipe and then re-entering your main exhaust chamber 180 degrees out of phase. And why the phase shift is important to cancel out the exhaust noise, we can show in this graph here. The blue line can represent your main exhaust chamber, and the red line can represent your J-pipe phase shifted by 180 degrees. You can see the wave doesn't start until right here. And if we look at the amplitude of the waves at different points along this graph, you can see that the two waves cancel each other out. So let's take this point for example. The amplitude here is 1. The amplitude here is -1. If you add these two amplitudes together, it equals 0. So, by adding a 180-degree phase shift of your exhaust tone, the overall amplitude, or the average amplitude, is 0. And this is how we are able to cancel out the noise in your exhaust. By adding this extra chamber, you are causing the wave to travel a total of 1/2 wavelength there and back, which can be expressed as 180 degrees. You are creating a 180-degree phase shift, which causes the amplitude of these two waves in your main chamber and the J pipe. When they come together, the amplitude is 0. This is how we eliminate exhaust drone. So, now you may be wondering, how do I know the frequency or the wavelength of my exhaust drone? Well, if you noticed in the beginning of the video, you may have saw some graphs overlaying the cold start and the driving shots of the car. And what these graphs are spectrums. It's a frequency spectrum of your exhaust tone. And while I was recording this spectrum on my phone, you can see that the waveform is peaking at 70 hertz, 80 hertz. It changes obviously with the speed of the car, but you can see here that this large peak is what I want to isolate and cancel out in my exhaust. To find the frequency of your exhaust drone, I recommend following the same method that I chose, which is downloading this application called Spectroid, and that will show you the frequency spectrum of your exhaust, and you can choose which point you want to isolate in your exhaust. So let's go back to this first equation that we learned. We know the frequency. We know the frequency by measuring it with the mobile application, and we know the speed of sound because this is a known figure. But one important point to note is that the speed of sound varies with temperature. And this is very important because your car operates at different temperatures based on how hard you drive it, based on the temperature outside. And I'm going to show you now how to make this calculation to find the length of your pipe. But first we need to talk about the speed of sound. Speed of sound at 20 degrees Celsius, I believe, is 331.4 meters per second. Now, this equation here shows how the speed of sound changes with respect to temperature. TC is temperature Celsius. Over an operating temperature of 100 degrees Fahrenheit to 500 degrees Fahrenheit, the length of your J-pipe varies pretty drastically depending on what you choose for your operating temperature. So don't just pick some random number, actually measure it. And I'll show you why in this graph. On the bottom, we have frequency. Let's look at 70 hertz. And on the y-axis, length of pipe. You can see that from a difference of 100 degrees F in the bottom here to 500 degrees F, the length of your pipe varies from 50 inches to 68 inches. So over an operating temperature of 400 degrees difference, the length of your pipe can actually change by almost 20 inches. So it's really critical to make sure you're using the correct temperature in the calculation for speed of sound. So after you've been driving for a decent amount of time, so your engine gets up to temperature, what you are going to want to do is measure your exhaust temperature. And what I'm going to use is just a standard infrared thermometer. And I'm just going to stick it in the end of the pipe here. And that should give you a pretty good estimate of what your exhaust temperature is. And once you know the temperature that your exhaust operates at, you can use this Excel tool that I've built. I will put the link to the Excel spreadsheet in the description of this video so you can make these same calculations. So we're going to scroll down this column, temperature in Fahrenheit, to 350 degrees. Now the spreadsheet is going to make this calculation automatically for speed of sound. So the speed of sound at 350 degrees Fahrenheit is 437 meters per second. The next step is select the frequency that you want to eliminate. We know that my car, the frequency I want to eliminate is 70 hertz. We're going to scroll down this column. We're going to scroll over from 350 degrees Fahrenheit, and here is the value of the quarter wave resonator or the J pipe that I should install in my car to cancel out this frequency. 61.5 inches. And that's it. That's the calculation. It's pretty simple once you have the understanding to make it. However, I do want to talk about if you don't have the ability to measure the frequency of your exhaust, you can actually calculate it based on your cylinder configuration. So the frequency of your car's exhaust can be expressed as the RPM times pulses per revolution of the engine, then converted to seconds. A 4-cylinder engine has 4 ignition events per cylinder. This equates to 2 ignition pulses per revolution. 8-cylinder engine has 4 ignition pulses per revolution. A 10-cylinder engine has 5 ignition pulses per revolution. All you really need to know here is take your number of cylinders and divide it by 2. And by doing this, you can actually calculate the frequency of your exhaust. So let's verify my previous measurement through this method. I told you that I want to eliminate noise between 2,000 and 2,500 RPMs. Let's scroll down in this column to 2,000 to 2,500 RPMs. You can see I took the average value. The frequency in hertz for a 4-cylinder engine, 70.8. And you can see that that's very close to what I measured, well within the margin of error. So this validates my calculation. I should say that I highly recommend using the mobile app to make this measurement over the calculation by cylinder, because this is an approximation. It's not going to be the same for every single vehicle. I'm sure you've heard a Subaru Boxer engine. That's a 4-cylinder. Now compare that noise to a Honda Civic 4-cylinder engine. They're completely different just because the way the engine is designed and the internal components and whatnot. So you can do this calculation, but just know that if you have a car that doesn't fit this generalization, it may not be that accurate. So I highly recommend using the mobile application. So let's make a quick summary. The equation wavelength equals speed of sound over frequency is the key to making this calculation. Frequency you can measure using the mobile application. Speed of sound you can calculate using the Excel spreadsheet that I will provide. And by adding a pipe that is 1/4 wavelength, you are introducing a phase shift of 180 degrees into your exhaust so that the tone that you want to eliminate looks like these two waveforms, and they completely cancel each other out. You can use this spreadsheet, link in the description, to calculate the length of your pipe. You can use this mobile app to find the frequency, or you can use this calculation to calculate the frequency. Hopefully you understand how this method works and you are confident and prepared to do the same on your vehicle. I'm going to be having this installed on my car in about 1 week, so I will definitely take some more videos of the performance afterwards and also show you guys what the pipe actually looks like under the car. So I just picked the car up from the shop. I drove it back here, then I drove it around the city a little bit to film some more shots inside the car, and I have to say the drone piping worked perfectly. The drone is completely eliminated between 2,000 and 3,000 RPMs, which is basically what I was going for. The shop did an amazing job installing the piping. It looks really clean. I will put a link to the shop in the description, but let me show you what it looks like. So here we're underneath the car. This is the rear passenger wheel. This is the muffler, and here is the drone piping. You can see it comes out of the muffler right here at 90 degrees and then bends this way. And there's actually 3 180-degree bends, and right up here is where it stops and is capped at the end. So as you can see, really nice welds, high quality stainless steel piping from Vibrant, and overall just looks really great on the car. Not only does it work well to eliminate drone, it actually looks pretty cool. So all said and done, I'm really happy with the work that the shop did. And it turns out the calculation I did was in fact correct. The drone was eliminated between 2,000 and 3,000 RPMs. Now, when I'm cruising around the city and shifting gears a lot, there's no excessive drone. It sounds really nice inside the cabin. So when I get up into the higher RPMs and hit wide open throttle, the car still is as loud as I would like it. So this modification only reduced the drone in that specific range and not any other RPM. One thing I did forget to mention in the first part of the video was that actually the way sound waves work, I am also eliminating drone at 2 times the frequency that I calculated and also 4 times the frequency that I calculated. So just by the nature of how waves work, when you have a signal at a certain frequency, it will produce what's called harmonics. And basically it will produce the same signal at 2 times the frequency, at 4 times the frequency, and so on and so on. So by eliminating my drone at 70 hertz, I'm actually also reducing noise at 140 hertz and 280 hertz. And that's just a side note. You may notice a slight change or reduction in some sound levels at double your frequency and 4 times your frequency. Just something to keep in mind. But overall, to conclude the video, this worked really well. It eliminated drone where I wanted it, but the rest of the range of the exhaust still sounds really good. So I hope that I was informative and presented the information in a way that you can understand. Of course, if you have any questions about anything, put them in the comments. Make sure to check out the shop's Instagram page. They do some really cool work. Great place. I'll probably be taking my car back there. It worked great. I'm really happy with the results, and thanks for watching.